Next of our formulae, formulas, whatever the plural is, the slope formula or the gradient formula, which hopefully you will recall. Different ways of doing it. I suppose the first time we looked at it, we simply just said, oh, well, it's the rise over the run. So however high up we go over how far across. And so here's a number plane. There's a line, which I've called L. There's a point on it. I've got a couple of coordinates. The formula comes from rise over run, because of course the vertical rise would be the difference in the y values, and the horizontal run would be the difference in the x values. Now, unlike the distance formula, the order is important. In the distance formula, it didn't matter because we ended up squaring. So we always end up with a positive answer. But in this case, we must keep it in the same order. So whichever point we have chosen to be y2, then its corresponding x coordinate must be x2. So subbing in 5 minus 1 over 5 minus 2, we have a slope of 4/3. There is another way of finding the slope, of course. There's another line. Now what I know about this line is it makes an angle of 120 degrees with the positive side of the x-axis, because the other formula for slope is slope is equal to the tan of the angle. And if you think about it, rise over run, if we were to draw in that right angle triangle, I'd be saying, opposite over adjacent, which is tan. So that's why there's another way we can do this. So the angle has to be going to the positive side. So it's always on the right-hand side of the line. In this case, I've got an obtuse angle, and that means I'll get a negative slope, because the tan of an obtuse angle, of course, is negative. And so tan of 120, it'll be minus root 3. But I could now work out the angle that that red line makes with the x-axis, because we worked out the slope was 4/3. So if I call that angle alpha, I could say, well, I know the tan of alpha must be the slope of that line, which we just found to be 4/3. This will be an approximation, of course, because 4/3 is not one of our exact values. And we get alpha is approximately 53 degrees. Two lines are parallel if and only if they have the same slope. So no, I did not misspell if. That is the correct spelling for if. It means if and only if. And what that means is the theorem reads the same backwards as forwards. But so some theorems read both ways, some only read one way. In this case, we can go either way. If I know they have the same slope, I can say they're parallel. If I know they're parallel, I can say they have the same slope. And for perpendicular, the way I like to say it is their slopes are the negative inverse of each other. Or a neat way of saying that, I suppose, is they multiply together to give -1. So here we go. A, B, C, and D are these 4 points. Problem is, I don't know the x-coordinate of this last point. We're going to find the x-coordinate of that last point such that AB is parallel to CD. Well, if AB is parallel to CD, I know their slopes are going to be the same. Slope of AB turns out to be 2. Slope of CD turns out to be 2 on A minus 3. But we've been told they're parallel, so therefore those slopes are equal. And solving that little equation, we get, well, A must be 4. So the x-coordinate is 4. Whereas if they were perpendicular, now I'd say, well, if they're perpendicular, I know they multiply together to give -1. And so solving this new equation, we get A turns out to be -1. Here's a classic question. You may have seen one similar to it in the past, where they give you 3 points and they tell you that those are 3 points, 3 vertices of a parallelogram, and you have to find the 4th vertice. Now, there's different ways of doing this. I think the quickest way is to simply draw a picture. If I draw a picture, so there's A, B, and C, and I'm told A, B, C, D is a parallelogram. Now remember, in geometry, the naming is very important because it's telling you the order of the vertices. So we go around in the direction A, B, C, D, and we must get a parallelogram. That's telling me, well, there's AB, there's BC, that's telling me that D must be down here. Couldn't put it up here. I could create a parallelogram where D is up there, but it wouldn't be the parallelogram ABCD. If I put it up here, it'd be the parallelogram ABDC. So as I say, the naming of the shape is quite important. The long way people go to finding D, they say, well, it's a parallelogram. So the slope of AB is the same as the slope of CD, so they find the equation of the line CD. They then say the slope of BC is the same as the slope of AD, find the equation of AD, solve them simultaneously, you come up with the point. Well, we don't need to go to that effort. Because the shape is a parallelogram, we know the slope is the same, and that's all I need to know. So I'm saying, well, to go from B to A, because these lines are also equal in length, because opposite sides of the parallelogram are equal and parallel, then to go from C to D, I must also go across 3 and down 5. Slope's the same. Oh, well, C was -3, -5. So if I go across 3 and down 5, D is the point, not -10. A lot quicker than going and finding all those equations and so on. I know people sometimes hate drawing diagrams, but sometimes drawing a diagram can make a problem so much easier. It's very hard to avoid doing coordinate geometry without drawing a diagram when you think about it. Now, if I want to prove 3 points are collinear, collinear of course means on the same line. Co, together, linear, line. So together on the same line. I want to prove they're collinear. How I do it? Well, I'll find the slope between 2 of the points. So for argument's sake, I'll pick A and B and find that slope. I'll then pick another pair. So for example, A and C. Now, if those slopes are the same, I know the lines are parallel. But they both contain the point A. So they can't be parallel. They've got to be the same line. And so that's enough to show that they are collinear, to show those slopes are the same. Ooh, yeah. 5B. Now it's time for you to play.